All right, let's keep going. So we've realized now that we do have some control over our path through the system, and we can see how we can map out a trajectory for ourselves, and how we can design reactors and interstage coolers, and how we can change the gradient and so on. And so we should have some confidence that we can reach. Well, it's hard to say any point on this, but we can move around in this space. And at this stage, it's not completely clear what we're going to do with this amount of freedom. I mean, it feels currently like, well, we could pick any inlet point. We just need a heater or cooler to the reactor train. So we could start anywhere here, and we could react, and we could cool to any degree, and so we could go wherever we like on this plane. And of course, we would like to pick a trajectory that is to some extent optimal. So we have to define what we mean by that. And typically, we are trying to reduce the volume of our reactor system. We normally, if we can reduce the volume of our reactors, that normally means the expense is reduced. So it could be the volume, and that so we could try and reduce the capital expense of the system. It could also be the overall conversion. So let's say our reaction mixture consists of components which are difficult to separate. So if they are difficult to separate, it would be much better to convert as much as we can to the product range. So if we have a high concentration of product, then there's less separation to do. So in the case where it's difficult to separate the components, it will probably be more optimal to choose something like that. So what we will do is try to establish how we can achieve the highest possible reaction rate, and in a sense that accomplishes both things. Because if we can get a high reaction rate, then we need smaller reactors to achieve the same overall conversion. And of course, if we can get a nice high reaction rate and a high conversion, then we'll have a high concentration of product as well. So I've prepared one of our isorate lines with this additional adiabat here as well. So let's say this is an adiabat, and remember we draw these adiabats from this equation. So that's the equation of an adiabat, and the gradient of the line is simply this factor. And so I'm claiming now that we have fixed the inlet flow ratios and so on. And of course, the heat of reaction is fixed, so the gradient is the only thing that's fixed. And so we are now free to choose an inlet temperature, and we are free to choose where to stop along the lines and so on. So let's now try and construct a way to optimize our trajectories through the system. So here's the line, and if we consider this adiabat, right? So we've fixed the slope of this line, and we're thinking now about a CSTR type arrangement. So let's say we've picked the entry temperature to be some value, let's say here. So let's say we pick the entry temperature to be this value, then of course the adiabat becomes this line. And now let's try and think about where the optimal point might be to stop along this line. And if we look at the values on the isorate contours, we can see there's this green line here, and there's the red line over here. And the green line is something times 10 to the minus 6, and the red one is times 10 to the minus 7. So we can see the closer we are to the green line, to the green isorate line, the closer we are to the value of 10 to the minus 6, and the more we move away from it, the closer we will be to the red line. So we are 10 to the minus 6 here, and then as we move down along this line, the rate is going to decrease and become more like this value 10 to the minus 7. So moving down here is a reduction in the reaction rate. Moving up here also is a reduction in the reaction rate. So going up here, we are moving closer and closer to that red line, and so the reaction rate is going down there. So clearly, the highest reaction rate along this line is at this point right here. So uh, where this line is a tangent to this green line, we have the maximum reaction rate. So let's mark that as a useful point to know about, right? And then let's move our line again. So if we think about the line here, you can see this time the blue line is 10 to the minus 5. So we've got the value of 10 to the minus 5 here. And then when we go above 10, when we go above this point, when we are around here along this line, we are closer to the green line. So that's 10 to the minus 6. So we are 10 to the minus 5 here, and then if we go below, we are moving away from the 10 to the minus 5 and going closer to the 10 to the minus 6, so that's also a reduction. So once more, the maximum value is at the point of tangency with this blue line here. And then let's move our adiabat again, and here we can see again this is 10 to the minus 7, and when we move away from 10 to the minus 7, we are going closer to 10 to the minus 8, so that's another point there. So let's mark off this point as well, and then let's look at this last point. So we don't seem to have another adiabat. You could say we are going closer and closer to equilibrium, where we know the rate is identically 0, so obviously that's getting much worse also. So the best point along this line is this point. So we could say, well, then we've identified a locus of points along which we will achieve the maximum possible reaction rate. So we could draw a line like so. Right, my aim is not great here, but I'm going to call that the maximum rate line now. So, so that's our maximum rate line. And you see this rate line is it is specific to this gradient. Of course, if we had a different gradient on this line, and let's just rotate it a bit to see that. So if we had a different gradient here, then you can see we would reach a different point of tangency in each case. So this maximum rate line, the location of this maximum rate line is dependent on the slope of this line, and the slope of this line is dependent on the ratio of this theta CPI, sum of theta CPI to the heat of reaction. So but if we do say, all right, that is my adiabat line, then this is the maximum rate path for us. So that at least gives us some optimal region to shoot for. So we can say we've got a very undesirable region here. This equilibrium line is where the reaction rate is 0, so we definitely don't want to be there. On the other hand, we've also identified this highly desirable region where we can maximize the reaction rate. And so we now want to design our CSTR to accomplish these nice small reactors. So we could say, well, if we start down here, we can get a little reactor, and we will be able to accomplish this conversion very quickly because the reaction rate down here is pretty high. But let's say we take a more reasonable conversion. Let's say, or let's just say the feed temperature is 350 degrees. So we say, all right, that's the entry value then. And so we're going to sketch in our first reactor. So we'll say, all right, that's going to be our reactor. We are going to sit here on this maximum rate line. So the entire reactor will be operating at this nice high reaction rate. So that's good. And then let's say we could cool down, let's say, well, all the way to 250 Kelvin. And by the way, I'm just using 250 because I know I want to do a bit of stepping up here, but in reality, we would never use such a low temperature because we typically do want to operate the reactor. We don't want to refrigerate things. It's expensive to cool things down on a plant because then you need an additional refrigeration system and so on. So normally we shoot for returning to 300. So you can get away with 300 Kelvin using a cooling tower or something like that. But anyway, for the sake of this illustration, we'll cool to 250. And so that defines how we'll be entering the second reactor in the train. And now let's shift this line. So that's our entry point now. And so our new adiabat line looks like this. So let's draw that in. Excuse my steady hand. Okay, so that's where the next reactor will be. And then, of course, we want to pull that down to 250 again. So that's there. And then let's shift the adiabat again. And so we've got a new reactor here. So that is then the best way to draw our set of CSTRs. So with 3 reactors, we can get to something like 55%. We might want to increase that. We could, but we probably won't get as high a conversion. So a conversion increase. So this might not be worth doing. It might be better just to separate. But anyway, this is then a way to pick a trajectory on our reaction plane. So we can identify a maximum rate line, and then our CSTRs, each of them will be operating at the maximum possible reaction rate. So that is one thing that we can do. So if we want to accomplish small reactors, we can operate on this maximum rate line. Another rule of thumb that has crept in is that we could identify how far we want to stay from the undesirable region. So we know the undesirable region is this equilibrium point where, on balance, nothing is happening. So we could say, well, we can't reach that point because we know that's a zero. We'd need an infinitely large reactor to get there. But a simple rule of thumb is just to stay 10 degrees short of that line. So if we know that we are starting at 350 degrees and that's our adiabat, then the equilibrium point that you could say the system is shooting for is that point. So we can say that point corresponds to that temperature. So if we take a value, say here, then that would be where the system would be at 10 degrees. So an alternate, let's use a different color. So an alternate is to say, well, let's take a path that leads us to this point, and so that will give us that means this won't be a small reactor anymore, right? Because the rate is much lower here. Right here, you have a much higher rate than here. But we've now accomplished a greater conversion with this reactor. So we accept this. So if we change the optimality criterion, so instead of trying to achieve small reactors, we say, okay, if we want to reduce the number of reactors, then we need to accomplish a greater conversion. So we can't be optimal in terms of reaction rate anymore, but let's push conversion as far as we can without running into serious volume problems. So let's take it there. So we are going to cool back now from this point to 250 degrees. And then we have to identify where the 10-degree point is. So we look along the adiabat again. So we can see from this point, the system is tending to that. So looking down here, that's around 220, that's around 320, that's around 310. So looking up here, we want to start somewhere here. So that's this line. Oops, I should have started here. So that's Let's correct that. So that's what the second reactor looks like. And then we can cool back from here to 250 again, and you see we are now slightly above that point. And oops, I've drawn that on the wrong layer. So so we are going to cool back from here to this point, and then we look for the next adiabat. Okay, I've drawn that on the wrong layer. Anyway, let's just draw it over there. So that's that reactor. Okay, and then let's shift our adiabat up here. Shift the adiabat here, and now you see we accomplish pretty much the same conversion as we had in that first case. However, we've done it now with 3 reactors. So you see here, we've taken 10 degrees short. So we don't have a small reactor anymore, but we've got a higher conversion. And we cool back, and then again, we use the 10-degree criterion. And then we cool back, and you see we reach a slightly higher conversion. And in fact, we could go a bit further and stop this only on 10 degrees and be consistent with our way of with our algorithm. But in terms of explaining this thing, and in terms of proving that you do get a smaller number of reactors like that, that serves the purpose. So we accomplish a smaller number of reactors, and that could have multiple benefits. So in addition to just having one less reactor to be concerned with, that also means all the control and instrumentation and maintenance and piping and all of that, that's all reduced just by allowing ourselves to have bigger reactors. So you might think this is a more undesirable case, but actually um, capital costs are not as high as operating costs. So the capital cost will be higher because we need bigger reactors here, but the operating cost, which is a continuous cost, that will likely be lower. So probably the second criterion is the better solution. So just to recap, in the first case, if we want the absolute smallest possible reactors, we've got the maximum rate line, and we can operate along that. If, on the other hand, we want fewer reactors with the same overall conversion, then we can use the 10 degrees short of equilibrium line. Of course, in that case, we do have to double check, especially in regions up here, whether this rate is not too low that we require ridiculous sizes of the reactor. So we have to be sure we don't have kilometers tall reactor requirements. So if we can get away with reasonable size reactors over here, they won't be as big as these ones, but as long as they are of a reasonable size, this is probably the better one to go for. Right, so that's CSTR design. And the same thing applies for the plug flow reactor. And I should have drawn this at the beginning, but of course, all of this is referring to reactors in some kind of train. So we've got a reactor here, and then the interstage cooling, and then another reactor here, and so on. Right, so that's what we're trying to design. And so now that we have these trajectories, we can calculate the volumes, and we can estimate the costs and so on. So we could actually propose both designs and just evaluate the costs in each case for operation of, say, 5 years. And we can decide just purely in terms of cost of operation whether to use this arrangement or the other one. So that's a CSTR. So in the CSTR case, the entire reactor is operating at these endpoints, and that's what we use to calculate the volume required. And these reactors, they could also be PFRs. So the same procedure applies for the plug flow reactor. So that's specific to this arrangement. Now, we could consider an alternate to this. We could say, well, what about the fact that our reactants could be pre-cooled? What about instead of using a separate heat exchanger, right? What about trying to maintain a high concentration of the reactant? And now let's consider an alternative. Let's say instead of having one long train of reactors where all the material enters the first reactor, let's try to use the cooling capacity of the feed stream. So let's say our feed stream coming in had a nice low temperature that we could use to cool the subsequent reactors. And in addition to cooling these other reactors and cooling them back down here so that we could keep reacting up, in addition to doing that, we would also have the advantage of staying in this region which has a higher reaction rate. So we would tend to gravitate back to this instead of progressing along in this direction. We'll see from the mass balance that we tend to cool back to this region where the reaction rate is higher than out here. So if we can do that, it looks like we can achieve even higher reaction rates. So to do that, we would take our fresh stream and let me draw it slightly differently. So here's our fresh stream coming in, and let's say we split off a side stream to the first reactor. Then subsequent to that, we also split off lines to the second and third reactors. So let's just split it here. So in this case, we are, of course, cooling back down. So remember, when the reactant comes through here, the exothermic reaction is going to push the temperature up. So the temperature coming out here will be higher than the temperature there. But then we are going to get this stream coming through, which is the same as the temperature over here. So this lower temperature mixes with this higher temperature. So the temperature will drop. Also, the concentration of the reactant will go up because we are adding this fresh stream of reactant in at this intermediate point, and the same applies here. So we get the lower temperature going in here and a higher concentration of A. So we restore the reaction rate and we restore the temperature. And you might say, well, why didn't you just do that in the first place? And the reason for that is, of course, then we are going to get a lower conversion, right? So remember, we've defined the conversion in terms of the fresh stream here. And we are looking at the concentration here, or the molar flow rate here minus the molar flow rate there. And if we are adding reactant in as these side streams, then we are going to get a reduction in the product. Sorry, we are going to get an increase in the reactant flow rates here, and that's going to cause us to lose conversion. So we consider cases like this when it doesn't matter that we have a high reactant concentration exiting here. So if we can tolerate a high reactant concentration, then we consider this situation. And there are indeed situations where this is possible. So if we consider, for example, ammonia synthesis. So remember, ammonia synthesis is three nitrogens, sorry, not three nitrogens. It's nitrogen plus three hydrogens, giving us two ammonia. So ammonia is has a significantly higher boiling point than hydrogen and nitrogen. So even though we might be feeding nitrogen and hydrogen here in these streams, it's very easy to remove these from the product stream. So this product stream coming out here, we can easily strip out the nitrogen and hydrogen from the ammonia. It's not an expensive step to do that separation. So we can get a very high concentration of product through an extra separation step, and that won't be an expensive step. So this is the kind of technology, or this is a suitable reaction set for this type of arrangement. Of course, in this type of arrangement, we then have to consider the shift in mass balance here. So when we add reactant here to the reactant plus product coming out here, there's a little mass balance to do here, and another little mass balance to do here. And you can also imagine that as we increase this flow rate here and here, the stream becomes closer to the inlet concentration. So when you mix a stream here with a high flow rate of a stream here, concentration in this line becomes approximately the same as the concentration here, and the temperature as well. So in this case, the situation looks more like this. I'm just going to hide a couple of these lines. So in this case, it's going to look something like this, right? So let's say we come in here and the reaction takes us in this direction. And then let's say we are cooling back to here. So in this case, when we cool back, it won't cool back along this line. In this case, the conversion will also drop. And so we would cool back something like that. And then the reaction may happen like this. And then we would cool back towards that point. So this point is basically our fresh stream. So let's just switch that on. So this fresh stream, which is available at this temperature apparently, and this and of course a zero conversion, we are mixing more of that stream in. So we are going back along this line. More the bigger the flow rate of those streams. So we progress along like this. And here you can see that apparently we aren't accomplishing much. It looks that way, right? Because we don't seem to be increasing in conversion as much as in the other case. And that's because we seem to be going down in conversion here. But remember that when we talk about using a high flow rate through here, that also means we are pumping in a high molar amount of reactant, and that reactant is being converted then. So in this case, although the conversion stays low, we do actually convert in absolute terms, in terms of total amount of flow rate here, we are actually converting a lot of reactant to product. And so the conversion is staying low, which means we are also staying in the high reaction rate region. And so we get small reactors here. So this way we are able to convert a large amount of reactant in a relatively inexpensive set of reactors. It's just that we do need an extra separation step. So we might be happy coming out with even 30%, because we know it's very easy to separate off the reactant, so we can still get a very high purity of our product. So we can take this route if we know it's very easy to separate the product from the reactants. So that is the only time we can tolerate a low conversion. Otherwise, we are trying to go high up in conversion here. So this is a third possibility, we can say. So in the first cases, we had talked about, we had established a way to work with small reactor volumes. So this red line gives us very small reactor volumes. Green line gives us fewer reactors, but they will be larger. And the blue line, that's about easy to separate components, and we can address high flow rates and get away with small reactors. You can see we are staying generally closer to this high rate region. Okay, so this applies to CSTRs and PFRs, right? The same comment we can make for the CSTR and PFR. And of course, it's just that when we calculate the actual volume, the calculation will be different. So we've already talked in detail how we would calculate those volumes, right? So that's the case for the the CSTR and PFR. Let's talk about the batch reactor. So let's just hide some of these. Unfortunately, I don't. Okay, so let's leave it like this. So let's say for the batch reactor, for the batch reactor, we can think about what's possible in terms of. Okay, so let's now develop this for the case of the batch reactor. Let's consider that for the batch reactor, it is possible to consider heating and cooling. So let's say we have a heating coil here. I'm just going to draw it here. So we can put in a heating coil, excuse me, and we could put in a cooling jacket as well. So we could have a high flow rate of cooling water here. And so obviously this is a batch reactor. There's no flow of reactant and product across the walls here, but there's this jacket. So we can flow things around the jacket without disturbing the reactor content. So we get good cooling heat transfer here, and we could add a heating coil here also. So this means we could, if the system is responsive enough, in other words, if the thermal lag is fairly low, then we could be getting a situation where we could control the temperature quite precisely. So what that means is that we could be at some stage. So let's say we've reached this point in the batch reactor. So we've managed to convert the reactor the reactant to a certain degree. So to 20%, we've converted 20% of the reactant, and we've reached the temperature of 400 degrees here. So what we are saying here is that if we apply heating fast enough, or if we apply cooling fast enough, we could move this point around. We could change the state of our batch reactor left and right like this. And obviously, in reality, it takes a certain finite amount of time to accomplish that heating and cooling. And while that's happening, of course, the conversion will rise because the reaction rate is positive in this zone. So it's probably more like this rather than an actual horizontal movement. But anyway, let's consider that ideal case where it is possible to get a lateral movement. So if we do have infinitely fast heating and cooling in our reactor system, we can say that we are moving left and right here, that before the conversion changes much, the temperature can change quickly. So if that is true, then let's consider this line, and let's consider this point here. Right now, you can see if we choose values of temperature that are greater than this, in other words, if we start looking in this direction, you can see we are moving closer to equilibrium, which means the reaction rate is going down. And also, if we look to the left here, so if we look at lower temperatures than this, you can see that we are moving closer to the green line, which is a lower rate line. That's 10 to the minus 6, whereas this blue one is 10 to the minus 5. So it looks like the maximum rate in this case, right, when we are looking horizontally rather than on the slant like we looked at before along the adiabat, right? If we look horizontally, then the maximum rate point is here at the maximum on this curve. And we can apply that reasoning to all of these, right? So on this green line, if we move to the left, we are getting closer to the red, and the red is 10 to the minus 7, whereas the green is 10 to the minus 6. So that's a lower rate region. And also to the right of that, we are again moving closer to the red line, moving closer to equilibrium. So that's also a lower rate region. So this is again the maximum rate region. And then on the red line also, over here to the left, it's closer to that, which is a lower rate, and to the right, it's also closer to that, and that's a lower rate. So that's again a maximum. and that's a maximum for the same reason. So you see, for the batch reactor, it looks like our maximum rate region is this locus of points. So we would like to stay on this set of points here. And we could imagine a situation where we could control the temperatures in or the heat contributions from these two. So we could change the flow rate here, and we can change the resistance on this electrical heating element, let's say. So we could control the temperature of our reaction mixture. And so let's say we start here, just for example. Now, of course, if we don't apply heating and cooling initially, then the system is going to try to reach equilibrium. So let's say it tries in this way. So the system heats up, and then we could detect, okay, if so if we know we are going to do that, if we know we won't apply heating or cooling initially, then we'd be able to say, well, then the system is going to, to rise along this line, and we can actually predict at what time it's going to intersect with this maximum rate line. And so we can say, okay, we'll reach this point, and then clearly the rate will continue to rise. But if while that, the conversion will continue to rise, but while it's rising, let's say we keep cooling the system. So if we predict, okay, it's going to take 10 minutes to get to this point, and so after 10 minutes, we must start cooling the system. And we must cool the system so that um, we stay on this line. Right now, see, at this point, we need to, so at this point, we have a fixed reaction rate. And so we know how fast the conversion is rising here. So if we know how the conversion is rising, how fast the conversion is rising, then we know, let's say after 1 second, where it's going to be. So let's say after 1 second, it's going to be here. Then we know, okay, that identifies this point on the line. So I must cool in 1 second enough for me to get to that point, and so on. So you can say, okay, then I can reach here. And then if I look 1 second into the future, let's say that means conversion. So looking at the reaction rate here, that means conversion will rise to here after 1 second. So then I must be over here. So I need to apply enough cooling to do this. So in this way, we can actually design a control strategy that will shift us along this line. And because this is the maximum possible reaction rate, we will then achieve as fast a conversion as possible. So that's how we can optimize for the batch reactor as well. So these are all the strategies that we can apply in optimizing our trajectory along or on this XT plane, so through these isorate lines. So we can see there are different optimality criteria that apply. Do we want small reactors? Do we want few reactors? Do we want, is it possible to get away with low conversions? Is it a batch reactor where we can apply lots of control? So under all these considerations, we can come up with intelligent ways of picking the best possible trajectory on this plane.